Welcome to this session on the Kronig Penney Model. This model is one of the simplest ways to understand how electrons behave inside solids. By the end of this talk, you will see how the repeating structure of atoms in a crystal changes the possible energies of electrons, and how this leads to the formation of energy bands. In the Kronig Penney model, we imagine a solid as a line of barriers and gaps that repeat over and over again. Physically, the barriers represent the regions near the atomic nuclei, where the electron feels a strong positive pull. The gaps between the barriers represent the regions where the electron can move more freely. This repeating pattern mimics the structure of a crystal lattice. Because the potential repeats, the electron wave functions are also forced to repeat in a special way, which changes the energies the electron can have. Here we define the repeating structure in terms of distances. The free space between barriers has width A, and each barrier itself has width B. Together they make up one unit cell of the crystal. The total length, A plus B, matches the spacing between atoms in the real lattice. The important physics here is that the crystal's repeating symmetry forces electron wave functions to obey Bloch's theorem. This means that electrons are not localized to one region but extend across the entire crystal, with a repeating pattern built into their wave nature. When we solve the quantum equation for this system, we see two types of wave behavior. In the free region, the electron wave oscillates, just like a free particle wave. In the barrier region, the electron wave either decays if its energy is too low, or oscillates with a different frequency if its energy is high enough. This behavior shows two important physics concepts, free propagation and quantum tunneling. Tunneling means that even if an electron's energy is less than the barrier height, its wave still penetrates into the barrier instead of stopping abruptly. At the point where a free region meets a barrier, the electron wave must remain smooth. Both the wave itself and its slope must match on each side. Physically, this rule ensures that the electron has a continuous probability of being found and that there is no sudden break in its current flow. This is the physics of conservation of probability. It also explains why electrons do not simply stop at barriers but can partly reflect back and partly continue forward, similar to how light partly reflects and transmits at a glass surface. When we apply these conditions to the entire repeating chain, we discover that electrons cannot have just any energy. Instead, the physics of interference allows certain energies and blocks others. The allowed energies form continuous ranges called energy bands. The blocked ranges form band gaps. This result is deeply physical. The electron waves interfere constructively at some energies, allowing propagation, and destructively at other energies, preventing propagation. This slide shows the band structure that comes out of the model. The allowed regions and forbidden gaps are easy to see. The physics here is wave interference inside a periodic system. The electron behaves like a standing wave in a crystal, and at certain energies, those standing waves cannot exist. That is why gaps appear. The size of the gaps depends on the strength and width of the barriers. Stronger or wider barriers create larger gaps, while weaker or thinner barriers allow wider bands. Now we can connect the model to real materials. In metals, the allowed bands overlap, so electrons always have available states to move into. That is why metals conduct electricity easily. In semiconductors, the gap between the valence band and the conduction band is small. With some energy, such as heat or light, electrons can cross the gap and conduct. In insulators, the gap is very large, so electrons cannot cross under normal conditions. This simple picture explains why different materials show such different electrical behavior. The Kronig Penney model is a simplified version of reality. Real atomic potentials are not perfect rectangles, and electrons move in 3 dimensions, not just one. But the physics is the same. The repeating nature of the atomic lattice forces electron waves into Bloch states and naturally creates bands and gaps. More advanced models, like the nearly free electron model or the tight binding model, improve accuracy, but they are built on the same foundation as the Kronig Penney model. The key physics lesson here is that energy bands are not an artificial idea, they come directly from quantum mechanics in a repeating system. Without a lattice, electrons act like free particles with continuous energies. With a lattice, their energies split into groups with gaps in between. This shows the direct connection between the microscopic world of atoms and the macroscopic behavior of solids. It explains why electrons in a crystal cannot simply take any energy but are confined to specific ranges. To conclude, the Kronig Penney model gives us a clear and simple picture of how solids gain their unique electronic properties. It shows how the periodic arrangement of atoms leads to bands, gaps, and the classification of materials as metals, semiconductors, or insulators. Even though the model is idealized, it provides the essential physics that underlies modern electronics, from transistors to solar panels. Understanding this model helps us see the deep connection between quantum mechanics and everyday technology.